This question is taken from the NSAA 2020 Section 1 paper, and it is question 38 of the Physics subsection. So we read, a solid sphere has density ρs, radius r, and volume v. It falls through a liquid of density ρl. Three forces act on it: weight, drag force d, and upthrust u. The magnitude of upthrust is equal to the weight of the liquid displaced by the sphere. So immediately you should think that the volume of the liquid displaced is v, the same as the sphere when it goes into the liquid. Drag d is given by d equals krv, where v is the sphere's speed and k is a constant. What is the terminal speed of the sphere? So we want to calculate the terminal velocity, which is when there is no net force. So whenever you think of terminal velocity, we should immediately think of no net force, no resultant force. So in order to get this question under grips, we should try and draw the forces acting on the ball. So it's falling down, so the weight is going down, upthrust going up. That's why it's called upthrust. And then we also have a drag force which should be against the velocity. So velocity going down, so the drag force would be going up. If it was the opposite way, if it was floating, then the drag force would be going in the same way as weight. So the force going down, the weight, must be equal to the two forces that are trying to reduce the motion's downwards velocity. So ρs vg, which is the weight of the ball, because this is mass times gravity, equals krv, the drag force, and then ρl vg. So v is the volume of the liquid displaced due to the ball, and then the mass would be ρl v, and then the weight would be ρl vg. So if we rearrange this for v, we get v equals ρs minus ρl vg, so taking that to one side and then dividing it by kr. So this is our expression for the terminal velocity, which is g. So this velocity is quite interesting. We can see that it depends on the density of the ball and the density of the fluid it's falling in, its velocity, and then gravity as well, and then k and r. So it's inversely proportional to k and its radius. So the answer is g for the terminal velocity expression.